to talk about molecular drawing today. Okay, we'll review some of the rules that we've gone over before, and then we'll practice. Practice makes perfect. You guys are awfully close without practice, but okay, molecular drawing. Rule number 1, obey all rules. Rule number 2, obey rule number 1. I'm waiting for this thing to come on. Here we go. All right, molecular drawing. The first thing we do, rule number one, is we draw a simple skeleton using all single bonds. So we're going to we're going to start with a simple skeleton using all single bonds. After we draw that, then we complete the octet. Making sure that each atom has 8 electrons around it. We complete the octet for all non-hydrogen atoms. Hydrogen can only have 2 electrons. It can only have 1 bond, so it can only have 2 electrons. We're not going to be adding any unbonded pairs of electrons around hydrogens. Around everything else, though, we will. Okay? So we draw a simple structure using all single bonds. Then we go back and we check all of the non-hydrogen atoms and make sure they all have 8 electrons around them, using dots and lines for bonds. And things to remember. Oh, then we compare total valence electrons. And where does total valence electrons come from? From the periodic table. So we use groups 1A, 2A, 3A, 4A, 5A, 6A, and 7A. Those tell us the number of valence electrons in those groups. Yes?
Yes.
So just quickly, how many valence electrons in group 7A, each element? 7. Group 3A? 3, 2, 1, oxygen, sulfur, selenium, 6, and so forth. So we need to know the total valence electrons. So all the atoms that are involved in the molecule that we're drawing, we need to total those all up. And that total valence electrons has to equal the number of electrons in your drawing. When you have a drawing where the number of electrons it contains is equal to the total valence electrons, then you can assume I drew it correctly. Okay? If you have more than one drawing that fits, if you have, let's say, 2 or more drawings, that are correct, in other words, you see that you can draw a particular molecule a couple different ways, and when you check the total valence electrons and compare it to the number of electrons in each one of these differently drawn molecules, same formula, and you realize they both work, then you have to go to formal charge to evaluate which molecule is the correct one. So if you have 2 or more drawings that are correct, we use formal charge to decide. And we'll practice that several times. We use formal charge to decide which drawing is correct. Which drawing is correct? Things to remember and consider while you're drawing these things. Remember that carbon has how many bonds? All right, it'll always have 4. It'll always have 4 bonds. When it has less than 4, like let's suppose it has a triple bond, that will be something unusual and very minimal, like the cyanide ion has a carbon, a triple bond, and a nitrogen. It has 2 unbonded electrons on each of the carbon and the nitrogen. It has 1 negative charge. What's another one that's an example of an exception where carbon doesn't have 4 bonds? Anybody remember the other one that we talked about? Carbon monoxide. Carbon monoxide is C triple bond of 2 electrons outside the oxygen and 2 electrons outside of the carbon. So that's an exception to the fact that, or the rule that carbon always has 4 bonds. But the majority of time, carbon has 4 bonds. You need to remember that when you're drawing the simple skeletal structure using all single bonds. If you see that carbon is going to need a double bond, then don't put a single bond, right? A couple of other things are rarely central atoms. Are they sometimes? Mm-hmm. Yes, we're going to have one. We've had one, if you remember, it was ClF3, chlorine trichloride. We'll draw that one in a little while to look at that one. Another one is elements with high electronegativity. Electronegativity being the tendency of an atom to attract electrons to itself. If an element has a high negativity number, like fluorine has what number? 4. Oxygen? 3.5. Nitrogen and chlorine? 3. 3.0. Carbon? 2.5. Good. Hydrogen? 2.1. And those are the ones we use the most. But if it has a really high electronegativity, then it normally is not a central atom. Okay? So elements with high electronegativity, normally not central atoms. And then that's something you just need to remember while you're drawing the simple skeletal structure. You don't want to put it in the middle to start with unless it really has to be there. Okay, so while you're drawing these things, you draw a simple skeletal structure that has all single bonds. You complete the octet for all non-hydrogen atoms. You check the total valence electrons from the periodic table with the number of electrons in your drawing. When that is correct, you have a drawing that is acceptable. Let's try some. We'll try one we've already done. CO2. So start drawing that one. Carbon dioxide. Simple skeletal structure with all single bonds. Except, while you're doing all single bonds, remember carbon has how many bonds? 4. And that halides and high electronegativities are not normally central atoms. So since you have a carbon, you want to make sure it has 4 bonds. There's only one of the carbons and 2 of the oxygens, so you're not going to put an oxygen in the middle as a central atom. Alright, so a lot of you have it drawn. So after you draw it, the rules say check the total valence electrons. Go to the periodic table. What is the total valence electrons? What's the valence electrons? How many valence electrons does an oxygen have? 6. We have 2 of them. That's 12. And 1 carbon, that's 4. So that's 12. 4 is 16. So TVE for this molecule equals 16. Did everybody put carbon in the center?
Yes.
So carbon in the center with an oxygen. When you do the single bonds, you'll realize right away, hopefully, that you need 2 doubles because carbon has to have 4 bonds. So we'll put a double there and a double there. Now, the next part of the rules say draw a simple skeletal structure, then add dots to complete the octet around each non-hydrogen atom. How many dots or pairs of dots are we going to put around each oxygen? 2. All right, 2, 1, 2, 1, 2. 2 pairs of electrons. And you add them kind of like in the shape of what a trigonal planar type shape around, even though they're terminal atoms and don't have traditionally a geometry. Or in valence shell electron pair repulsion theory, they don't have a geometry. Only the central atoms do. Alright, that's it. Now we want to check the total valence electrons with the electrons in the drawing. TVE is 16. I'm going to count the electrons in the drawing. 2, 4, 6, 8, 10, 12, 14, 16. So when total valence electrons is equal to the number of electrons in the drawing, you have a drawing that is an acceptable rendering for this molecule. So TVE equals 16 from the periodic table, and that is also equal to the number of electrons in the drawing. Alright, I want you to draw CO, Cl2, CO, Cl2, like cockle-2, isn't that a bird? No, it's a cockatoo, it's a bird. Alright? Little bird brain, yeah. So we have COCl2. You have to decide what the central atom is going to be. It's not a hard decision on this one. What do you think, Anna?
The carbon is the central atom, and then you have to have a double bond connected to the oxygen.
Could you have the double bond connected to one of the chlorines?
No.
I mean, you could have. Why wouldn't you want to necessarily?
Because then you couldn't complete the octet till negative.
Well, how many electrons does chlorine need to complete the octet around it? It's got how many valence electrons? What group's it in?
It has to have 4 groups and 8 electrons.
Look at the group number that chlorine is in.
7.
7A. Alright? So, it has 7 valence electrons. It only needs 1, it's chlorine, to get to 8, right?
Yep.
Oxygen has how many valence electrons?
8. Oh, 6.
6. It needs 2 to get to an octet.
Yeah.
So the double bond would go more easily with the oxygen than with one of the chlorines, right?
Yes.
Alright, so you are correct. You're going to put the double bond with the oxygen. Carbon, double bond oxygen, single bond to each chlorine. What is the geometry going to look like here? The electron, the molecular geometry, trigonal planar. So you might as well start out drawing it like that, right? On the test, they're going to require you to make sure that you draw the molecules using or utilizing your skills and your background to get the correct molecular and electron geometry. So we're going to put the carbon in the center, a single to each chlorine and a double to the oxygen. And I'm going to put them closely separated by 120 degrees each, so it's somewhat trigonal planar. We're going to put my trigonal planar. So this is boron trifluoride or boron trihydride, and it is trigonal planar. So you want to draw this COCl2 somewhat trigonal planar, so that you end up with about 120 degrees angles, 120 on each angle, 120 degrees on each angle. I forgot to complete the octet on all non-hydrogen atoms. So how many dots go around the chlorines?
6.
All right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Around the oxygen? 4, okay. It already has 4 because it's sharing electrons. In covalent bonding, we share electrons. What happens to electrons in ionic bonding? They transfer. That's how you get ions. One atom loses electrons. The other atom gains electrons. So the electrons are transferred. That forms ions. So ionic bonding is formation of ions. Here we have sharing of electrons. So we need to do the TVE and compare it with the electrons in our drawing. The total valence electrons for 2 chlorines is 14, plus 1 carbon is 4, that's 18, plus an oxygen is 6, that's 24. So TVE is 24 electrons. We need to see if our drawing has 24 electrons. I see a problem here. Let me add one more dot here. 2, 4, 6, 2, 4, 6, 2, 4. All right, so I'm going to count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 23.